Chemistry, and you are watching M Science.
For 9701 Chemistry A Levels question paper 4-2 of the examination series October-November 2022, we have already solved first 4 questions, that is question 1 to question 4, and in this video we'll further solve few more questions. So here is question 5, and the question 5 is related to the transition elements. Let's read it. Copper is a transition element. It forms a wide variety of compounds. Now the question A says define transition elements. So just write directly straight a 1 mark definition which says that it is an element. It is an D block element. It is a D block element. It is a D block element with one or more stable ion. It should have some ions with incompletely filled d orbital. The ion should have an incompletely filled d orbital, and that is the main definition of a transition element. Let's go ahead with the B part. Now definitions are few points which you should learn. So I would recommend that for A levels, if possible, learn all the definitions which are commonly asked, like what is a transition element, what is a ligand, and you will come across few more definitions. If you learn these definitions, you'll get cash marks, which definitions generally carry 1 or 2 marks for each one. So let's go ahead with the B part. It says an aqueous solution of copper 2 sulfate contains CuH2O6 2 plus complex ions, and if an excess of concentrated hydrochloric acid is added to this solution, a ligand exchange reaction occurs and the complex given here is formed. Now complete table 5.1 to state the geometry. Geometry is the shape of and the coordination number of copper and one bond angle in each of the 2 complex ions. Now the complex ions are given here, which is an aqua copper complex ion, and the second one is chloro copper ion. Now as we can see that H2O is 6 H2O ligands are bonded to copper, so obviously the geometry, the shape is octahedral. When there are 6 ligands, the only shape possible is octahedral, and so the coordination number is 6, and if it's an octahedral shape, the bond angle should be 90 degrees. Now chloro complex of copper. Now you can see that there is 4 chloro ligands bonded to copper. Now the only 2 possible geometry is either square planar or tetrahedral, but let's be specific. Chloro forms a tetrahedral geometry with the copper, so we'll write tetrahedral, and the coordination number is obviously 4 because there are 4 monodentate ligands bonded to copper, and if it's in tetrahedral shape, then the angle should be 109.5 degrees. Be specific, but you can definitely write in place of 109, you can write 109 to 110. That is also acceptable. Let's go ahead with the next part, where it says that in an isolated copper ion, the d orbitals are all degenerate. In a complex ion such as copper aqua complex, the d orbitals are non-degenerate. Define degenerate and non-degenerate in this context. Now what is degenerate? They are the orbitals with the same energy. So what is degenerate? The orbitals with the same energy. The orbitals with the same energy, and in the same way non-degenerate are the orbitals with different energies. That is the definition in this context. Let's go ahead with the third part. Explain why the solutions of the two complex ion in table 5.1 are different colors. Now these two solutions are of different colors and the question carries only 1 mark. If it carries more marks, then we need to explain it in detail. But as it carries only 1 mark, we can write it in short that the two complex ions absorb the different wavelength of light from white light, we can say from white light, and hence exhibits different color. Complex ions absorbs different wavelength from white light, and so they are of different colors. Next, go ahead with the C, where it says Cu2 plus forms a complex ion containing water molecules and ethane diovate ions. Now ethane diovate ions are shown here. It is C2O4 2 minus as ligands. The formula of the complex is given here. The ethane diovate ion is a bidentate ligand. Now explain what is the meaning meant by bidentate ligand. It's a ligand. It is a ligand, or you can say it's a species which forms two coordinate bonds, or you can even write two dative bonds, two coordinate bonds with the central metal ion. Central metal ion in a complex also you can write, but this much is enough for a 1 mark question. And let's go ahead with the next parts. Here it says 3 stereoisomers with the formula CuC2. Okay, this is the formula given with a 2 minus complex. Complete the 3-dimensional diagram to show these 3 stereoisomers. Now you can see that H2O are only 2 ligands and ethane diovate are also 2, but then ethane diovate is a bidentate ligand. Now let me be specific. Draw a C2O4 bidentate ligand. The structure should be something like this. Okay, so these are the oxygens which have lone pairs, and these two oxygen forms the coordinate bond with the copper. So if we be specific, then what I'll say is that we can have a trans and cis isomers. Trans cannot have an optical isomer, that is it can't form a mirror image, but cis will form a mirror image. So let me draw trans first here with two H2O molecules opposite to each other and a bidentate ligand with oxygen here. Okay, so this is ethane diovate ion and this is a trans isomer of the copper ion. Oh sorry, here I would draw, and here are 2 oxygen atoms. So let me write this is a trans isomer, and if we draw a cis isomer here, obviously then H2O cannot be opposite to each other. So H2O molecules should be, let me be specific here, because I always prefer that the atom which forms the ligand should be pointing towards the copper. So again I made a mistake, and so I've rubbed out H2O1 here. So here again I'm drawing another H2O which is cis, and the remaining bonds will be occupied by the ethane diovate ions. So I'm drawing here the ethane diovate molecule with the structure here. Again this is O and O bonded with 2C, and those 2C again bonded with the double bond O. Now the mirror image of this is going to be the second isomer of this, that is H2O should be pointing here, another H2O on the top, and the remaining bonds occupied by the ethane diovate ion. So again oxygen and carbon double bond O on the carbon. Here again an oxygen, carbon, carbon, and the double bond O on both the carbon. Now you can see that how did I have drawn the ethane diovate ligand. I have seen students getting confused how to draw a bidentate ligand. So I always prefer that the atom which forms the coordinate bond should be written first, and that will give you an idea that how to draw the remaining part of the molecule. So now these are the two cis molecules which are mirror image of each other. Now let's see what comes up next after the isomers. Okay, there is one more question where it says, use your answer to C2 to answer this question. Stereoisomers 1, 2 and 3 show two different types of isomerism. Name these two types of isomerism, and for each type of isomerism identify the pair of stereoisomers that demonstrate this isomerism. So as I have specified, we have drawn two types of isomers, that is cis and trans, which we can also write as geometric isomers, or even you can write cis and trans isomers, and the second one is optical isomers. Now if you talk about optical isomers, then let's see that what are the two optical isomers which we have named. Okay, stereoisomer 1 and 2 are the optical isomers that are mirror image of each other. So I'll write stereoisomer 1 and stereoisomer 2, and the geometric isomers, that is cis and trans isomers of each other, we can say either 1 and 3 are the stereoisomer, or even we can write 2 and 3 are the stereoisomers. So let me write 1 and 3 here, they are the geometric isomers of each other. Now if we again, let's go ahead with the D part, where it says a solution contains 3.70 gram of a sodium copper complex dissolved in 100 centimeter cube of solution. A 25 centimeter cube sample of this solution is warmed and then oxidized by 0.010 mole per dm cube acidified potassium manganate. Here the equation for the redox reaction is shown. Calculate the minimum volume of 0.01 mole per dm cube of acidified potassium manganate needed to oxidize all the ethane diovate in 25 centimeter cube sample. Show all your working. So we are supposed to work out for this 25 centimeter cube of solution only of the ethane diovate solution, and the molecules, that is we are given the mass of the copper sodium complex given here. So and we can see that the MR, that is relative molecular mass, is also given. So the first thing which we will calculate is the moles of the complex ion, moles of the copper complex ion. So that is mass upon MR, molecular mass, which is 3.70 divided by the 321.5, which is 0.0115 moles. Now we have found out the moles of the complex of the copper. Fine. Now if we go ahead, we need to look at the equation. Now the equation shows a mole ratio of the manganate and the ethane diovate ion. Now if we look at the formula of the ethane diovate ion, we can see this complex, that if the moles of the whole complex is 1, the moles of ethane diovate ligand is twice. We can see that each complex ion contains 2 ligands of ethane diovate. So the moles of ethane diovate, I would say C2O4 2 minus, should be double than the moles of the complex. So we need to multiply it by 2, which is 0.0230 moles. Now this many moles are in 100 centimeter cube, but we are supposed to calculate for 25 centimeter cube. So the moles of ethane diovate in 25 centimeter cube, then we need to divide these moles 0.023 divided by 4 to get the moles in 25 centimeter cube. and the answer is 0.00575 moles. Now we have already got the moles of ethane dietine. So again have a look at the equation where we can see that the mole ratio is 5:2. So if we want to calculate the moles of manganate ions from this, then we need to multiply the same moles first by 2 and then divide it by 5, which gives us the answer of 0.00230 moles. From these moles we need to calculate the volume required of 0.01 mole per dm cube concentration. So if we have a look at the formula, if we want to calculate volume, then volume should be moles divided by concentration. So now if we have got the moles, it is 0.00230 divided by the concentration 0.01, which gives us the volume of 0.230 dm cube. But our answer has to be in centimeter cube, so multiplying it by 1000 we get 230 centimeter cube. I hope the calculation is very clear, where we have calculated the moles of complex first and then the moles of ethane dietines, from which we calculated the moles of manganate, and from the moles we calculated the volume. So let's go ahead with the next part, where it's copper nitrate and barium nitrate both decomposes when heated. Copper 2 nitrate decomposes at a lower temperature than barium nitrate. Suggest a reason for this difference. Now if we talk about the decomposition temperature of carbonates and nitrates, as we had already done for group 2, we can relate it with here also. And we had studied that the decomposition temperature increases as the size of the cation increases. I repeat that the decomposition temperature increases if the cation size increases. Cation size increases. So if we compare here, it's written copper nitrate decomposes at a lower temperature. That shows that the copper ion should have a lower ionic radius, or you can say that the copper ion is smaller compared to the barium ion. So then barium ion, and hence as copper ion is smaller, copper ion will polarize the nitrate ion more, and hence the decomposition temperature is lower, which I am not writing here, but you can elaborate it and write it. But as it carries 2 marks, these are the 2 important points you need to mention. So here our question 5 ends. Let's go ahead with the question 6. Question 6 again seems to be something related to some cobalt copper complex. We read an aqueous solution of cobalt chloride is pink color due to the presence of cobalt H2O6 complex ion. Complete the table 6.1 to describe what is observed when the named reagent is added to an aqueous solution of cobalt 2 chloride. Now cobalt 2 chloride is pink in color, that is specified, and the reagent added is NaOH. Now we know that when we add an aqueous NaOH to any transition element, it shows a precipitation reaction, and so the OH is added as a ligand. So we can write the color cobalt containing product. So color, if it is aqueous, it generally shows blue to pink, but if it's a precipitation reaction, so I would say that the state will be solid and the color remains pink because it is solid. Now if we write the color of the aqueous solution, then it will turn blue, but as I'm specifying it's a solid substance, it's not aqueous, then I'll write pink. Okay, an excess of concentrated HCl solution, now it's going to turn blue because HCl, it will form an aqueous solution and the state will be aqueous. So This is the color and the state of the cobalt containing product. Next says write an equation for the reaction of the cobalt water complex with NaOH. So let's write an equation specifying this cobalt H2O6 with the charge 2 plus. Here we are adding NaOH, so I would specify OH minus. I'll balance the equation later on. First let me write the formula of the complex. Here the ligand of water becomes 4 and the OH ligands are added 2. So the complex charge becomes neutral because the cobalt charge is 2 plus and OH are added twice. So 2 minus added, so the neutral now. So 2 OH I'll balance here. Now 2 water molecules are removed, so 2 water molecules in addition. Now if you want to write a precipitation reaction, then you can also write the formula OH twice also and the 6 water molecules moving out. This also is allowed here, but as we are talking about the complex ion, so I prefer writing this reaction. Now next is write an equation for the reaction between the cobalt water complex ion and an excess of concentrated HCl. So if we are adding HCl, then chloro is the ligand which is added. So let me write the complex formula first and then let me write the chloride ions as a ligand added. But as we know, it will form a tetrahedral complex with the charge 2 minus. So the valence has to be here 4, and as all the ligand of waters are removed, so 6 water molecules removed out. So these are the equations where written for the two reactions. Let's go ahead with the B part of the same question. The B question says define stability constant. Now again a definition has come. As I said, few definitions you need to learn. So what is a stability constant? Stability constant in relation with the transition metal complexes, I'll say, is an equilibrium constant. So I'll write it is an equilibrium constant, an equilibrium constant for the formation of complex ion, for the formation of any transition complex ion. I have not specified a transition metal, but complex ion in a solvent. So this is the definition of stability constant. Now write an expression for the stability constant of cobalt ammonia ion complex ion. So if we are talking about an cobalt ammonia complex ion, then it would be formed from its ions, or would say the ligands added to the complex. So formation of cobalt amine complex, I'll write the species of the formula of the complex first on the top. And when ammonia is added to the cobalt complex, so the cobalt of the water complex has to be written at the bottom because that's the reactant. And when ammonia is added, so ammonia has to be the other reactant. Now the number of ammonia ligand is 6. So obviously 6 ammonia molecules are added. So the power has to be added with 6. Now give the units of the stability constant of the ammonia cobalt complex ion. Let me explain and work out the units here itself. If we say, okay, by mistake I've written 6 here, it should be 2 plus. Okay, if we have one complex on the top, it has to be moles per dm cube here. For the bottom also, for the water complex, we need to have moles per dm cube here, multiply by moles per dm cube 6 times. Moles per dm cube 6 times for ammonia. So there is a cancellation from top and bottom, and what is left is mole power minus 6 and dm cube. In place of dm cube we'll write dm power 18 because that goes on the top. So that is the unit for this stability constant. Now the numerical value for the stability constant of this ammonia complex ion is 7.7 into 10 power minus 4. Sorry, not minus 4, it's plus 4. And in an aqueous solution of concentration of cobalt ammonia complex ion is 0.0740 moles per dm cube, and the concentration of ammonia is 0.480 moles per dm cube at equilibrium. Calculate the concentration of cobalt water complex in this solution. So here we just have to substitute all these values in the above equation. So the stability value 7.7 into 10 power 4 is equal to the concentration of cobalt ammonia complex again. So that is 0.0740 divided by, again, water molecule complex we don't know, I'm writing it as X, into the 0.480 to the power of 6. Now that is the substitution of the complex, and then we need to find the value of X from this equation. This will give us the answer of 7.86 into 10 power minus 5 moles per dm cube. Now here is the end of question 6. Now let's go ahead with question 7 also. Now 7, it seems to be the organic part with the benzene ring structures. Question 7 says the structural and displayed formulae of 3 aromatic compounds A, B and C are shown in figure 7.1, and here are the structures. Compare the relative acidities of A, B and C. Now look at the structure. Now A has got one carboxylic ion group into the carbon chain. Now the next is a phenol compound where OH is directly bonded to the aromatic benzene ring, and there is one more carboxylic group in the carbon chain, but then in the adjacent carbon we have a chloro group bonded. Now a chloro bonded to a carboxylic increases the acidity. So because of the presence of chloro group, the compound C will be the most acidic, then will be the A, and B will be the least acidic because there is no directly carboxylic group bonded, it's only the phenol group bonded to the aromatic ring. That is, phenol is present. Phenol is definitely acidic, more acidic than other alcohols, but compared to carboxylic acids, it's weakly acidic. So if we explain the answer, we need some enough space for explanation. Let's explain here. C is more acidic because, let me specify here, C is more acidic because of the presence of chloro and electronegative oxygen, presence of which are electronegative, weakening the OH bond, and stabilizes the anion formed of the intermediate compound. Next is A. A is again acidic but less acidic. I'll say is acidic because of CO bond present, again electronegative, that weakens the OH bond, and stabilizes the anion, compared to be of phenoxide ion. Compared to phenoxide ion, the anion of A will be more stable. So I am specifying it here compared to the compound B of phenoxide ion. Let's see what's the next B question says here asked. So methyl benzene is given here, can be made from benzene by an electrophilic substitution reaction. Identify a compound that reacts with benzene to form methyl benzene and identify the catalyst used. So if we are adding alkyl group CH3 to the benzene, then the chloro group of the same alkyl compound should be taken. So the compound name which is added as an electrophile is chloromethane. Chloromethane, because a methyl chain is added. So chloromethane is the compound we'll use, and as we know the catalyst is common, that is aluminium chloride, or you can directly write the formula, that is AlCl3. The first step in the reaction is the generation of CH3 plus electrophile. Write an equation for the reaction that generates this electrophile. Now, there is a reaction between the chloromethane and AlCl3, the catalyst which generates this electrophile. So, electrophile CH3 plus is generated and the complex formed is AlCl4 minus. And in the third part it says describe the mechanism for the reaction between benzene and the CH3 plus electrophile, include all the relevant curly arrows and charges. So here if we start with, then the first curly arrows goes from benzene to the methyl electrophile, and because of that an intermediate ring with a positive charge will be formed, where the positive charge will be pointing towards the methyl group which is bonded, and here the hydrogen will also be present. Because of the presence of both the group hydrogen and methyl group, the benzene attains the positive charge. Now one more curly arrow from hydrogen to the benzene ring, where it is shown broken and the methyl ring gets completed, benzene ring gets completed with the methyl group bonded, and the H plus ion moves out. Now let's see the next question after the mechanism here. Identify a suitable reagent to oxidize the methyl benzene to benzoic acid C6H5COOH. That shows that the methyl group has to be oxidized to the carboxylic group here. Write an equation for this reaction using O to represent an atom of oxygen from the oxidizing agent. Now the only oxidizing agent to oxidize a benzene ring C6H5CH3 is the alkaline KMnO4. So equation has to be written down. Here we have to write alkaline KMnO4, alkaline KMnO4 plus heat. That is required. That's the reagent and the conditions required. Now let's write the equation here, C6H5CH3, and we are supposed to write an equation with the O. Let's see that how many number of oxygens we are adding here. So C6H5COOH is written here, and the carbon will or hydrogen will move out as water molecule. So we can see that here the methyl group changes to COOH, one carbon is as such, one hydrogen is used, and two hydrogen are still left from H3, that is done replaced by water molecules. So how many oxygen have we added altogether? 3 oxygen. So for the balancing we need to add 3 with the oxygen. Now the fifth part here, the methyl benzene and the benzoic acid are both nitrated with a mixture of concentrated nitric acid and sulfuric acid to give mononitrated products. The structural formulae of these products are the given here, 2 complexes respectively. Draw the structure of these 2 products. Now let's understand the question first. What we have done is oxidize the methyl benzene first. Now methyl benzene have a methyl group substituted on a benzene. Now methyl group is an electron donating group which will attract the incoming electrophile either on the 2nd or 4th position, and so if we nitrated, the nitro group will either go on the 2nd position or on the 4th position, but any one of the position will be occupied, so we can't draw both. So either of the formula or the structure will draw. And the second nitration is the benzoic acid is nitrated. Now benzoic acid is an aromatic group with a carboxylic group on the top. Now carboxylic group is an electron withdrawing group, so it will direct the incoming electrophile on the third or fifth position, and so the nitro group will move out here. So out of this second and fourth, we'll draw any one. So I'm drawing the structure with the nitro group on the second position, but as I have mentioned, you can draw it on the fourth position also. And the next structure with a benzene and carboxylic group on the top and nitro group on the third position. Are we supposed to name it? Just have a look at the question again. No, they've said draw the structures of these two products, so we don't need to name it, otherwise we could have named it. The 2-nitro-methyl-benzene and 2-nitro-benzoic acid can be named, but it's not needed here. So just let's go ahead with the next part itself, where C part shows a reaction scheme is shown in figure 7.2, where again we are starting with the nitro substituted methyl benzene. Reaction 1, it changes to amine. Here you can see that the nitro changes to amine group, and this amine then in the reaction 2 is changed to a diazonium chloride ion. That is again changed to a phenol group of the same methyl benzene, and in the reaction 4 a di is formed with the structure Y. The first part of this question says describe the reagents and conditions to produce the diazonium ion from the amine compound in reaction 2. So we are talking about this reaction where the amine group is changed to diazonium ion. And for the reaction conditions for this is the nitrous acid is required, and then we need a temperature between 0 and 10 degrees. The conditions here the conditions here should be written here, that is the temperature should be between 0 and 10 degrees Celsius. The second part of this question is describe how the CH3C6OH can be produced from this diazonium ion in reaction 3. So if we want to produce replace OH in place of diazonium ion, then we need to add water. So add water and warm, that is the temperature should be greater than 10 degrees. Warming with water with little more temperature, that will produce the replace the diazonium ion with the OH, or you can say the phenol is produced. Draw the structure of the di molecule Y formed with this diazonium ion and the phenol group when they react together in reaction 4. Describe the conditions for this reaction. Now if we look at the top part of this question, we had a benzene ring with the methyl group, and then we had substituted nitro group on the second position, if you remember, or you can always pause and go back and look at the structure. This was the structure we had made. From that we made the amine group. So here in place of nitro we substituted it with amine group, and that changed to the diazonium ion. And then there is a coupling reaction of these diazonium ion with the phenol group of this. So in short, I'll draw a structure where a methyl group is present here and an amine group is substituted here, which changes to diazonium on the second position, and this diazonium then have a coupling reaction with the phenol of the methyl benzene. So the benzene ring is directly bonded on this part. The phenol gets substituted, and here on the opposite side we have methyl group. Sorry, I'll draw the OH part on the opposite side of the diazonium or on the benzene ring, that is aromatic ring. The diazonium and the OH group will be opposite to each other, and as we had already substituted, the methyl group is besides the OH, that is OH should be on the second position. If we go ahead with the same structure and which is replaced amine, then changes to the OH. If we remember, that is the whole substituted process. The same methyl nitrobenzene was changed to the phenol of the methyl benzene. So if we go ahead with the same structure, CH3 and OH should be on the adjacent carbon of the aromatic ring, and so this is how the I'm drawing the structure. Now what are the conditions required for this? Now, as we know, it's a coupling reaction. We need an aqueous NaOH and also the temperature below 10 degrees. So, temperature below 10 degrees has to be maintained, because otherwise the diazonium will break down into phenol part again. So, these are the reaction conditions required for the coupling reaction. Okay, we have done with the 7th question. We are still left with 2 more questions which we will be solving in our next video.